Okay, so this article is related to development of stable data-driven POD. POD means reduced order model for the turbulent flow simulation. Basically, POD means proper orthogonal decomposition, and stability development of stable data-driven POD means we are just going to stable data-driven in proper orthogonal decomposition for the reduced order model for the turbulent flow simulation. So here is a turbulent flow simulation in terms of Berkows, one of the scientists who just introduced the proper orthogonal decomposition method for the analyzing of turbulent flows. Okay, the dominant spatial modes are extracted using the singular value decomposition. Okay, and their temporal evaluation is modeled. Okay, so in the derived reduced order system, which is integrated in time to predict flow dynamics at a fraction of computational cost of full order simulations, a robust implementation of dynamic mode decomposition is also employed for the comparative analysis. So in this section, we are just analyze the quantitative error analysis demonstrates that the regularized POD ROM provides the accurate reconstructions of the flow fields while maintaining the long-term stability. Okay? And the energy capture efficiency and model dynamics are assessed to validate, reduce the model performance. Okay. So here is the keyword with the introduction. Introduction, we have just used how the turbulent flow simulation remains challenging problem in the computational flow, and how we are using the investigation of the intermodal energy transfer in the POD and Galerkin representation of the turbulent separated flow, and how direct numerical simulation of the Navier-Stokes equation requires extremely fine computational grids through the small time steps. Okay, so this is the stable data-driven POD ROM visualization, and the 3D Navier-Stokes equations provide us the time stability and reduce the order of the model. Okay, and this one is also in the introduction. Let me just explain you how the high fidelity Taylor Green vertex data are used as a benchmark snapshot for the model construction and evaluation. And the comparative analysis basically in our case is between POD ROM and DMD. Prediction is performed to assess the reconstruction accuracy and stability. Okay, so here is a motivation and challenge. Motivation and challenge is that we are using our main motivation is that we are just going to simulate the central problem in fluid mechanics due to its complex spatiotemporal structures for full-scale simulation using the Navier-Stokes equations, which are computationally intensive and often practical for long-time or real-time applications. Okay, so here is basically the challenging is that we are just going to accurate modeling turbulence in the reduced space remains challenging, and the conventional basically Galerkin based POD models are often suffer from the numerical instabilities. So the proper orthogonal decomposition and the model analysis is that how which parameters and which energy modes are used in our POD cases, and widely used technique for the dimensionality reduction in fluid flows. Okay, so the next part is the data-driven ROM operator influence inference. So in that case, a data-driven ROM operator interference, we are just using the approach of formulation of the evaluation of model coefficients as a linear or nonlinear regression problem, and that research developed a reduced order modeling of the global ocean means POD, oceans using POD, and basically, okay, the basically this mitigates the issues caused by ill-conditioned snapshot matrices and the noises. Okay, so here is the dynamic mode decomposition as a complementary technique, and here is the ROM error with DMD error and the time span. And the objective of the present work is basically we are developing the stable data-driven reduced order model for the two-dimensional turbulent flows, high fidelity Tyler Green vertex simulations, which are used to generate the snapshot of dataset, and POD is applied to extract the dominant spatial modes, and the regularized linear operator is inferred. Okay, so here's a problem statement. Problem statement is that we are just facing a Navier Stokes solver is a computational expensive due to its high resolution required in space and time. So direct numerical simulation becomes impractical for the long-time integration or real-time applications, limiting its instability in control and the optimization task as well. Okay, so we need to overcome this instability through ROM, through this snapshot of dataset results in inaccurate predictions, and we need to overcome this POD-based reduced order modeling framework with regularization of techniques to ensure the long-term stability, and we just use the dynamic mode decomposition to validate the predictive accuracy as well. Okay, here is a mathematical model, mathematical equations used for incompressible Navier-Stokes equations. These are the Navier-Stokes equations, and these are next the functions of. Okay, high fidelity sniff. Okay, high fidelity snapshot is basically equations are presented here, and where the proper orthogonal and decomposition is applied through singular value decomposition. These are the equations used in it, and the methodology is stated here. So the methodology is basically developed for the, okay, this is basically dot, okay, dot A. Okay, so yes, DMD reconstruction are determined, and the MATLAB, yes, design and MATLAB simulation. In MATLAB simulation we are using different Bashford schemes to subsequent steps, and every time step we are using the vorticity is updated accounting for nonlinear advections and the viscous diffusion as well. So here is a simulation of parameters used in it, and time-dependent values of the dynamic mode decomposition with this is the output results of singular values with cumulative energy. Okay, and here is the main field and POD model basically, and this is output results of relative reconstruction error, and here is the field comparison U at snapshot, and model coefficients FOM versus ROM, and then results and discussions how the POD and dynamic mode decomposition in model reduction occurs, and how it provides us the stability, how it provides us the larger dataset accuracy in terms of prediction. So this is the conclusion and the references. Let me just open the MATLAB files. Let me run that MATLAB file. Okay, see the similar values cumulative energy, mean, POD mode, relative reconstruction error, field comparison US snapshot. Next figure is 5, which is basically this one is the model coefficients FOM versus ROM. Okay, these are the output results. If you need to ask anything, you just ask me, I will answer your questions.